Yeah. So these are the main textbooks or reference books, and this is the evaluation scheme. Quizzes or assignments 20%, and then each minor exam 20%, and the final exam 40%. Okay. So this will be the syllabus. SIPSA's book, first 5 chapters and then 7 chapter. 6th chapter is not there. We will try to cover all these chapters, but we may fall short depending on the time. We will try to see how much we can cover. Okay. So coming to the topic. So why theory of computing? This is one of the most fundamental courses of computer science because it helps you in understanding how people have thought about computer science as a science in the past century. See, you're not just computer engineering students, you're computer science engineering students. The degree which you will be getting is computer science and engineering, CSE. So you need to understand what is the science part in that, right? Building an app, building a website, all these things, they're not the science part. So what is the idea of computing or the idea of computation itself? You need to understand that. So what makes a computer, right? And it is not this machine which is in front of us. Okay, the idea of computer is more abstract. Someone said a computer is to computer science as a telescope is to astronomy. You see, buying a telescope does not make you an astronomer. Even without a telescope, you can be an astronomer. Okay, telescope is only a device. Similarly, the computers which you use are only devices. They don't make you computer scientists. So the idea of computation is something which you need to understand to be a computer science student. All right. And you will see it is relevant in understanding later compilers course, operating systems, even cryptography. Many of those things, they also have many theoretical aspects. So most of those theoretical aspects, the foundations, will be covered in this course. Okay, so you'll find this course relevant to many other courses later. So this is mainly a theoretical course, but a very important course. All right. So theory of computing can be broadly divided into 3 subtopics: complexity theory, computability theory, and automata theory. Complexity theory deals with how difficult or easy a problem is to solve. All right. Computability theory discusses whether a problem is solvable or not, solvable on a computer or not. Automata theory discusses different kinds of mathematical models of a computer. What are the strengths and limitations of each kind of mathematical model? What kind of problems each model can solve, right? So those kind of questions automata theory discusses. So let's get into each one of them, and you'll get a better idea as we go ahead. So first, let me begin with computability theory. So what does this deal with? This deals with the issue of which problems are solvable and which problems are unsolvable on a computer. Can you think of some unsolvable problems on a computer? Or some solvable problems on a computer? You know many. Adding to integers, searching a video, searching the web, Photoshop kind of a thing, creating an image, creating digital painting, many things you can do with a computer. Can you think of some things which you cannot do using a computer? Can you think of some problems whose solution is not there in the domain of computer? Huh? Opinion-based questions. Okay, fine. Yes. What else? Hmm. Traveling salesman problem. Yeah, it is solvable to whatever extent it is solvable. It is not like it is not. See, again, whether it is P versus NP is a different question. So I'll come to that later. But technically, one can find it. Okay. Anything else? It's not. It need not be something technical, like he said. But in general, your general understanding, okay, this doesn't come under the domain of a computer. Say all kinds of philosophical questions like, does God exist? Right? What is the meaning of my life? Right? Am I alone in this universe? These kind of questions. There is some uh, school of thought called solipsism, which actually says that how do you know that any other living beings exist? Right? You may see other bodies, so-called people roaming around you, but how do you know that they are conscious beings like you? What if they are all machines trying to act like you? Right? There is no way for you to know that they are conscious beings. You may know that you are a conscious being because you have self-reflection, understanding, whatever it is. But there is no way for you to know that others are also conscious. You are only inferring that they are conscious because they are behaving like you, right? But it's not a proof in itself. Okay. Now, I believe all of you might have, or at least most of you might have heard of ChatGPT, right? So you just look up ChatGPT online and start chatting with it. You will not believe that you're chatting with a machine. It will give answer to almost every question you ask in the in the most commonsensical way possible, and it also speaks in a very sensible way, right? It's as if you're speaking to a human. It frames a proper answer. You will not be able to know that you're speaking to a machine, all right, unless someone tells you that there is a machine on the other side. Okay, so you have no idea that there are other beings, other conscious beings in this world. There is no way to prove that. All right, so that is one problem which maybe even a computer cannot solve. Am I the only person existing in this universe, or there are other beings? Right? So there are many philosophical kind of questions which even a computer cannot solve. So not every problem is computational. There are non-computational problems and there are non-computational solutions. So which problems are solvable on a computer, which problems are not solvable on a computer, that is discussed in computability theory. Okay. Now, suppose I know which problems are solvable, like traveling salesman problem or 2 plus 2 equal to 4. There are many problems which are solvable using a computer. Now, within that, I also want to know how much time it may take, how much time and resources it may take to solve a particular problem, right? Which problems are easy to solve, which problems are difficult to solve. Okay, so that comes under the domain of complexity theory. So which problems are easy and which problems are hard. So this is discussed in complexity theory. So you would have already come across many examples of time complexity in data structures and algorithms courses. Like what is the time complexity of insertion sort? What is the time complexity of traversing a graph, or traversing a linked list, or switching a node in a linked list, or inserting a node in a linked list or an array, right? So each one of them has a time complexity. So that is an example of complexity theory, right? This is an easier problem compared to that. This can be solved maybe in linear order. This can be solved in polynomial time. This can be solved in exponential time. So if the same problem has two solutions, one in polynomial time and one in exponential time, then we obviously choose polynomial time because it will save us time and resources, right? There can be some problems which can be solved in a day or two. There can be some other problems which may take even years to solve. They are solvable in principle, but they will take a huge amount of resources to solve. For instance, like Bitcoin mining, right? Cryptocurrency mining. It takes huge amount of resources and machines. That's why people discuss environmental issues with cryptocurrency mining and all that. So they can't be done within a day or two. You need some hundreds or thousands of supercomputers running for days or months to mine some very few coins, right? So that's a very complex problem. Whereas adding two integers or multiplying two integers with million digits and million digits may be done within a day or two, right? So this is much easier. So maybe I will choose to spend my time and resources on this problem because this is solvable within a practical amount of time, whereas that is quite impractical. Although it is solvable, it is quite impractical. So I will not go that side unless it is really necessary. That's how cryptography also sort of works. You see, when we say, why do you think you are asked to set a password with so many constraints, right? It should have minimum this much length. It should be a combination of alphabets, small case, uppercase, digits, symbols, all these things. Why do you think that is the case? Do you think if you do that, someone cannot hack your account? If you don't do that, someone can hack it, but if you do that, someone cannot hack it. What is the trick here? What is the advantage of using so many symbols? Huh? Exactly. It just becomes harder to crack your password. All right. Just think. Suppose I have a 3-digit password and only digits. You need to use only digits. Now, all that one needs to do is to try all possible numbers from 0 to 999. One of these will be the password. All right. Now, just imagine if the length increases. So this 0 to 999 is how many possibilities? 1000. Why? Because each place can take 10 digits. 0 to 9, 0 to 9, 0 to 9. So 10 possibilities, 10 possibilities, 10 possibilities, 10 into 10 into 10, 10 cube, 1000. Now imagine you have 10 places and you use only digits. Then the complexity will be 10 power 10, right? Each place 10 digits. So 10 such places, 10 into 10 into 10, so on 10 times. So 10 power 10 different possibilities are there. Now, instead of just digits, now I'll add alphabets. I will add symbols, right? Imagine 10 digits plus 26 small letters, 26 capital letters, 62 plus imagine some 12 symbols. So 74. So now 74 possibilities are there in each place. So 74 power 10. So many possibilities one has to check to crack your password. So it is not that it can't be cracked, it is solvable, but the time and resources which a hacker needs to spend to crack one individual's password is much more costlier than the benefit which he is getting out of it. So that makes it a loss venture, right? So rather than spending so many resources on it, I will do something else, right? So this is only one of the things in cryptography. Again, it is more complicated with some key, private key, public key, hashing. Many other techniques are there. It's not this straightforward, but just for you to get an idea that having a longer password, having a more complex password does not make your problem any more unsolvable than having a simpler password. It is still solvable, but it is a bit harder. That's all. So it is only a degree of complexity rather than a degree of computability. Okay. So this is the difference between easy and hard problems. So that's why complexity is very important. Okay. And automata theory discusses all kinds of computational models, right? So whatever computer we see, it is based on the idea of an abstract model of a computer called Turing machine. We will get into that in a while. But before Turing machine, there are other computational models. So each of these computational models have a proper mathematical foundation, mathematical definition, and what are the limitations of each of these computational models and all those things. So automata theory provides us all the mathematical tools like set theory and all those things to define the computational model, and then computability theory lets us discuss which problems are solvable using this computational model, which problems are not solvable using this computational model. And then complexity theory helps us further by classifying within the solvable problems which ones are easy, which ones are difficult. Okay, so the order in which we will go is first we'll discuss automata theory, then computability theory, then complexity theory. Okay, but before we go there, first we need to discuss a slightly more meta level concept. So theory of computing is also known as formal automata theory. Okay, so formal automata means we are dealing with formal systems. All right. So can anyone give me an example of a formal system? Any formal system which you know of? What is a formal system, or what is an example of a formal system? You know already. Maybe you may not know that that is a formal system, but you know it. You have been dealing with it day in and day out, since your school. Any guess? Doesn't matter whether you're right or not. You're saying something? Huh? I can't hear you. Mobile phones. Okay.
Math.
Huh?
Is math a formal system?
What?
Is math a formal system?
Maths, mathematics. Mathematics is a formal system. Okay. Mobile phones is not a formal system. Formal system means it is mostly a theoretical concept, an abstract theoretical thing. It is a closed system. All right. Everything is well defined in that. Axioms and the rules, and then using these rules, you can derive new theorems from the axioms. Right. So such a system is a formal system. All right. Any other formal system you know of? Physics. Physics is formal because it's based on mathematics. Physics in itself is not formal system. In fact, physics is more open-ended because it brings in reality. Reality is not a closed system. You don't define reality. But formal system, you define everything. Okay? Reality is given to you. Formal system is created by you. Yeah, algebra, all these are branches of mathematics, so that all comes under mathematics. Yeah. Number system, again in mathematics. Sport or game is also a formal system. Sort of, yes and no. So let me tell you why. Any game you take, there is no way in which you can define every single possible rule, or you can imagine every single possible scenario of that game. You will need to update your rules as and when you encounter new scenarios. Say for instance, say two of us are playing chess. Now suppose I'm about to lose. What if I just throw away all the coins from the chessboard? This is not written in the game that you cannot do this. Once I do it, someone will add it. Okay, you can't do this, right? Otherwise, someone was thinking, okay, you should move this coin. I mean, this piece like this piece like that. Only those are written in chess rules, right? No one writes, okay, You should not blow them. You should not hit them. You should not hit the opponent. Right? I can always bypass the rules. Even if you write a million rules, I can always come up with a new rule which is not in this million. So a game, you can never define all the rules in the game. It's impossible. There are infinite possibilities. One can always bypass. There are always glitches and bugs in video games also. So they keep updating. Yeah, even the game writer may not know what will happen in the new scenario.
Sir, then how does a set of rules say that it's complete in the way that there can't be anything added to it anymore?
I'm not saying it cannot be added to it anymore. The point is, so I will come to that. So we will discuss some features of a formal system later: consistency, completeness, soundness, all those things. This question will be answered after we discuss that. So I'm not saying that a game or sport is not formal because all the rules are not defined in one go. They are not formal because there can be conflicting rules, and even the rules are incomplete. There can be conflicting rules, and the purpose is not served. It is served to some extent, but it is not served to a complete extent. Okay, so in that sense, even the formal systems which we know of, like mathematics and logic, they are also not completely formal because they also have loopholes. They are also written with something called paradoxes. Does anyone know of any paradox? Forget about maths or logic, but any paradox you know of? Huh?
Russell's paradox?
Russell's paradox, yes. Someone was saying something else. Grandfather's paradox, yes. So now in mathematics, so Russell's paradox is something which had shaken the foundations of mathematics. You see, foundations of mathematics is set theory. Everything, actually these systems are called formal because each one of them, I mean, another example of a formal system is logic. Propositional logic, predicate logic, right? These are logics. You know of propositional logic like truth tables, true and true is true, true and false is false, those kind of things, P implies Q, right? So these are all, they are also formal systems. There, the form is a preposition or a predicate. In mathematics, the form is a set. Entire mathematics is based on set theory. Any mathematical branch you take, be it geometry, algebra, trigonometry, group theory, ring theory, whatever you take, it can be reduced to sets. Everything can be boiled down to sets. Okay, so set is the most fundamental form in mathematics. And Russell had actually punctured a hole into the idea of a set itself. So before I tell you about Russell's paradox, I will tell you a simplified version of Russell's paradox. Say something like a library paradox. So imagine in the library we have two kinds of books. Books which contain their title inside, the content of the book, and books which don't contain their title inside. Okay. Now, if I have a book which contains the titles of all and only those books which don't contain the title inside, does this book contain its own title or not? I repeat, if I have a book which contains the titles of all and only those books which don't contain their titles inside them, does this book contain its own title or not? If it does not contain its own title, it should contain its own title because it should contain the title of all those books which don't contain their title. If it contains its title, it should not contain its title because it should contain the title of only those books which don't contain the title. So it should both contain and not contain its own title, which is a paradox. Right? So, and a paradox is not like any riddle where with some thought you can come up with a solution. No, paradox is fundamentally sort of unsolvable. It is a contradiction. Okay? So there is no solution to this. Right? So you cannot come up with any such book. If it contains, it should not contain. If it does not contain, it should contain. It always infers the opposite. It always implicates the opposite. right? Another simplified version of Russell's paradox is a barber's paradox. So imagine in a village there is a barber who shaves all and only those people who don't shave themselves. Now, does the barber shave himself or not? So if the barber shaves himself, he should not shave himself because he shaves only those who don't shave themselves. If he does not shave himself, he should shave himself because he shaves all those who don't shave themselves. Right? It's a paradox. So daily this is a dilemma for him. Right? So there are many such paradoxes. There are many paradoxes related to infinity. One such paradox is Zeno's paradox. Has anyone heard of Zeno's paradox? Yeah, what is Zeno's paradox?
Can an infinite number of infinitely small things add to a finite one? Something like that.
Sort of. So what he's saying is, can an infinite number of infinitely small things add up to a finite number? That's a very valid question. Simply putting, you have a real number line. Now, what is a Euclidean point? It's consisting of only Euclidean points, right? What is a Euclidean point? It is a lengthless, widthless, heightless point. Now, which means it doesn't have any extension. Now, when you put many such unextended points, how are you getting a line with extension? It's like you are adding zeros. No matter how many zeros you add, you should get a zero only. No. How are you getting a non-zero? So the only solution which mathematicians give is they throw in infinity into the mix and then say, okay, when you put many infinite zeros, somehow you will get a non-zero. When you put finite zeros, you will get a zero only. But when you put in infinite zeros, somehow you get a non-zero. We don't know how. That is the nature of infinity. Because these are infinite Euclidean points. When you take each individual point, there is no extension. But when you put infinite of them, somehow they are giving a line with extension. How? We don't know. And that line is infinitely divisible, which means between every 2 points, there are infinite points. This is the crux of Zeno's paradox, that motion is impossible. Because for me to move from point A to B, I should first reach the midpoint. To reach that midpoint, I should reach its midpoint. For that, I should reach further midpoint and further midpoint and so on. But I will never reach the midpoint of even the next point, because between every 2 points, there are infinite points. So motion is impossible. So that is Zeno's paradox. So, but it is counterintuitive, but it is logically sound. It's not a silly thing. It's not a silly argument. It's a very sound logical argument. For thousands of years, people have been breaking their head to resolve this. We know motion is possible, but logically it is impossible. How to resolve this? As long as you accept infinity, as long as you accept infinitely divisible reality, technically motion is impossible. Okay, so many such paradoxes are there. Another paradox is Arrow's paradox. Again, this is given by Zeno. Zeno gave many paradoxes. This is one. Arrow's paradox is one. He says, imagine I shoot an arrow. Now, imagine I take a snapshot of this arrow at different positions. I take thousands of photos or million photographs of this arrow in each position. Now, where is the motion? How do you distinguish between motion and rest? Suppose, when do I say an object is at rest? One simple definition is, if an object occupies as much space as its body has, then that object is said to be at rest. This is one simplified definition of an object being at rest. Now, if you look at this arrow's motion, in each snapshot, the arrow is at rest because it is occupying only so much space. So, inside each snapshot, there is no motion. Inside every snapshot, the arrow is at rest. Now, where is the motion happening? You may say between two snapshots, but between two snapshots, there are again infinite snapshots, again where the arrow is at rest. So, where is the arrow moving? So, arrow cannot move. Motion is impossible. Right? So, there are many such paradoxes. Another interesting one. It may look silly, but again, it's a survival related paradox. There is a donkey, which is a very logical donkey. It never defies logic. Okay, whatever it has to do, it first thinks logically and then only it acts. So there is a donkey, it's very hungry, and two haystacks are placed in front of it, both at equal distance, both of same size, equal distance, identical. Now, which one should the donkey go and eat? If it chooses one over the other, it is a logical absurdism, because logically both are equal. It cannot choose one over the other. So this donkey actually dies of hunger. It may look silly to you, but that's the nature of that donkey. It's a logical one. It cannot choose one over the other. There is no reason to choose one over the other. Both are at equal distance, both are identical. So it cannot make a choice. Okay. Another quick, simple one. I don't know. Some of you may have heard, not heard. Ship of Theseus paradox. Have you? Anyone of you heard? There's also a movie, Indian movie, Ship of Theseus. It's a very good movie. It's a brilliant movie. You should watch it. So Ship of Theseus paradox, it is related to the paradox of identity. So basically, it's a Greek paradox. So there's a Greek hero called Theseus. He defeats a demon and he's returning to his homeland on a ship. Now it so happens that it's a wooden ship and one of the planks gets spoiled. So he replaces that with a new plank. Now it so happens that almost every plank gets spoiled one after another, and he replaces every plank with a new one. Now by the end of it, is it the same ship or not? Okay, so that's one question. To make it more complicated, imagine I take all the old wooden planks and build a ship with it. Now, which is the original ship? The one with the new planks or the one with the old planks? So this again depends on which school of thought you come from. Do you believe that a whole is the sum of parts, or a whole is greater than the sum of parts? This is a school of thought, or this study is called mereology, study of parts and wholes. So if you believe a whole is nothing but sum of parts, then the moment I replace even one wooden plank, it becomes an entirely different ship, right? Because the sum has changed. Even if one part changes, the sum has changed, so the whole will change. So it should become a different ship. But in reality, we don't behave like that. You see, this table is there, something is chipped off, or some part is broken, or something happens. I don't say this is an entirely different table. I say this table, some portion of this table is chipped off. I will say it's still the same table, right? I don't say, okay, someone has put a different table here, or forget about table, even ourselves, our bodies. Always cells are being replaced with new ones. So then I should say every moment, okay, this is a new person, this is a new person. Oh, who are you? When did I meet you? We should keep greeting everyone every time. We should keep acquainting ourselves with every person every time. We don't do that. We treat that person as the same person, right? So maybe whole is greater than sum of parts. All right. So one may say, if the second school of thought, if one takes and then says, you see, the ship is not just made up of parts, it is greater than sum of parts, and the ship which is made of new planks is the original ship, because Theseus has been staying on this ship from the beginning to the end. If one says that, then what about the ship which is made up of the old planks? Does Theseus not have any connection or emotion with that? So is this the original one, or this is the original one? These are all paradoxes. They're not simple, easy to solve. Practically, we somehow lead our life as if life is simple. But once you start digging into the concepts, you will understand how complicated the concepts are. Or something as simple as time, like grandfather's paradox, which is like time travel and all these things. Most of the films you would have seen, they're all paradoxical. Once you bring in time travel, you are bringing in many paradoxes with you, right? So the concept of time, the concept of space, many things, the concept of parts, all these are paradoxical. All right. Another simple example, which is more relevant for you to understand, is a heap paradox. What is a heap? Suppose a heap of sand. What is it made up of? Nothing but sand granules, right? Now, suppose there is a heap. Now I keep removing one sand granule at a time. I keep removing 1, 2, 3, 4, and so on. At some point, the heap will vanish, right? Now, can you tell me at which point the heap becomes a non-heap? after removing which particular granule can you say that this heap is no longer a heap? No, there is no one such point, one such granule after which you can say that this heap is no longer a heap. Or the reverse, you are building a heap, adding one granule, one granule, one granule, and so on. At some time, this non-heap becomes a heap. When does it become? This is called boundary shifting problem, right? So when does a heap become a non-heap? When does a non-heap become a heap? Again, there is a problem. There's a paradox. Somehow we know roughly this is a heap, this is not a heap, but exactly we don't know when does a heap become a non-heap. What is the boundary between a heap and a non-heap, right? So there are many such things, many such interesting paradoxes in reality and also in mathematics and logic. So these are all paradoxes not just related to reality. There are paradoxes, many of the ones which we discussed now are related to reality, but there are also paradoxes related to mathematics. One of them is Russell's paradox. I gave you simplified versions, Barber's paradox and Legendre paradox, but a technical version of Russell's paradox is, imagine you have two kinds of sets, sets which contain themselves, sets which don't contain themselves. For instance, if I say set of people, so this set contains only people, it does not contain itself because itself is not a person. But if I say set of all non-people, then this contains all kinds of things, chairs, tables, laptop, this, animals, everything, including the set itself, because that is a non-person. Okay, so there are sets which contain themselves, sets which don't contain themselves. Now if I have to build a set of all those sets which don't contain themselves, does this set contain itself or not? That is the question. So if the set contains itself, then it should not contain itself because it should contain only those sets which don't contain themselves. And if this set does not contain itself, then it should contain itself because it should contain all those sets which don't contain themselves. So what is the concept of a set? Entire mathematics, the building of the structure of mathematics comes down crumbling because the foundation is shaky. Foundation is set theory. Set theory is based upon the idea of a set, but a set is paradoxical. So how can the building stand? But it stands. We don't know why and how. Building stands. We are working in it. We will work as long as the building is safe. It's working. That's it. That does not mean the foundations are foolproof. Foundations are still open. We don't know why the building is standing, but it's working. So let's work as long as it goes on. Okay. Similarly, logic, set theory, all these things are there. Okay. So the so-called formal systems, they are formal because conventionally they work. Conventionally, they have nothing much to do with reality. They are purely defined by us. They are purely based on symbols, and we have given rules to manipulate these symbols, and they follow those rules. That's it. Okay. Although within these rules, if you follow the same rules, you will still run into paradoxes. Like Russell's paradox is not bringing in any new rule. It is just taking the simple idea of the rules of a set. A group of elements constitute a set. That's it. There is a set and there are elements of this set. There is a relation called containing. A set contains an elements. A set contains elements. That's it. Just taking this simple relation, I have cooked up a scenario which seems paradoxical, right? I didn't violate the nature of the relation. The relation itself brought this kind of scenario. Okay, so although you are following all the rules, you may still run into paradoxes. Okay, but still this is formal because this is sort of artificial. You have created this concept and you have defined the rules. Okay, and it is working to a large extent. So that is the idea. Fine, but when you bring in reality, it's like language. There is a difference between natural languages and artificial languages. Like programming languages are all artificial languages. C, C++, Python, Java, all these are artificial languages. Formal logic is also an artificial language. Propositional logic, predicate logic. In fact, they have come up with these languages because natural language is ambiguous. So within formal languages, there are well-defined rules. You know where the ambiguity is, but still they have their own issues, but still to a large extent, they serve their purpose. All right. But they are closed systems. They are not affected by reality. In fact, they have no connection with reality in one sense. We'll see that in a while. So that is what makes these systems formal and useful because they are closed systems. Whereas the moment you bring in reality, it is an open-ended system. You don't know everything about reality. You don't know how reality will behave. You don't know if other universes exist. You don't know what are the rules on a different planet. You don't know what are the rules in a different universe, right? And you may revise your understanding of reality over a period of time. Like when Newton was there, people thought Newton's laws sort of applied to entire reality. But then later they found that they are not applicable to quantum level or atomic or subatomic reality. You need a different kind of physics there, quantum physics, right? So all these things are there. So we may see a new phase of reality later, based on which we will revise our laws of physics. Okay, but mathematics is closed. It's a closed system. It has nothing to do with reality. When you apply maths to reality, you will get physics. When you leave mathematics as mathematics, it's a formal system. Okay, so that's the idea of a formal system. So each formal system. So first of all, okay, so some examples of formal systems, mathematics. Propositional logic, predicate logic, and so on. This is not preposition, this is proposition. Okay, so a proposition is a statement which can take a true or false value. It is not one of the 8 parts of speech. Okay, a formal system has mainly 4 features. It can have one of these 4 or more than one or all 4. So soundness, completeness, consistency, and decidability. All right. So these are the features of a formal system. Okay. So before we discuss any of these features, we need to discuss one more concept. Difference between provability or validity and truth. So let's take a simple example and you will understand difference. You may have heard of this example or you may not have. Suppose I say all men are mortal. Socrates is a man. So what can I conclude from these 2 statements? Huh? Socrates is mortal. Now, these 2 are called premises and this is called a conclusion, and this entire process is called deduction. It's called deduction or syllogism. Okay, now this statement happens to be both valid and true. So it is true because we know all men are mortal, and we know if there is a person called Socrates, he will also be mortal. It's like we are comparing with the reality which we know of. So this is true in this reality. Okay, And this is a valid statement because it automatically follows from the previous two premises. Okay, so deduction is one of the, or probably the most important tool to come up with any new theorem or assertion or lemma or whatever it is. You start with some axioms, you perform some rules, and you come up with a lemma or a theorem. Okay, all that is basically a deduction. You start with some premises, you arrive at a conclusion. Now this conclusion will become a new premise for a further conclusion, and so on. All right, so this is one scenario, so let's call it scenario 1. Okay, let me copy it and discuss. Another scenario. So suppose I say I keep these premises as it is, but I change the conclusion saying Socrates is immortal. Okay, now first of all, is this true or false? Is this conclusion true or false? False. No man can be immortal. So Socrates is also not immortal, but the conclusion is saying he's immortal. It's a false statement. Okay, is it valid or invalid? Is it following automatically from the premises or not? Is it following automatically from the premises? If I give you two premises, all men are mortal, Socrates is a man, will you conclude? Will it, if you give it to a machine, does it conclude that Socrates is immortal? No. So this is both false and invalid. Okay. So this is another scenario. Okay, let's see one more. Now, let me change the premise itself. I will say all men are immortal. Socrates is a man, therefore Socrates is immortal. So what is this? Is this a true statement or a false statement? It is still false. It is not changing my reality. My reality will remain the same. So still Socrates is immortal is a false statement. Is it a valid statement or an invalid statement? It's a valid conclusion because it is following automatically from the premises. It's a different case that the premises, one of the premises itself is false. That's a different thing. But assuming this premise is true, you will get this conclusion if you follow the rules. Okay, so this is valid and false. Okay. Yeah, just 2 minutes. Now I will change only this premise. Now, is the conclusion true or false? See, truth has nothing to do with the premises. Conclusion by itself has a truth value. You just need to see whether it is matching with our reality or not. Is the conclusion true or false? True. Socrates is mortal. Is it a valid conclusion or an invalid conclusion? Invalid, because it will not follow from the premises. So, simple thing. For validity, you need to look at the premises. For truth, you need to look at reality. Okay? Both are different things. Validity has nothing to do with truth. Truth has nothing to do with validity. All right? So, this is invalid and true. Okay? So now what is the conclusion from this entire exercise? Logic deals only with provability or validity, not truth or falsity. The latter comes under the domain of reality. So the point is, logic need not be related to reality at all. It may or may not be related. You can come up with a logic which is related to reality, where your premises are true premises in this reality, or you may come up with a logic which is completely unrelated to reality. Like in my logical world, all men are immortal. Okay, I can just start with such premises, but the rules will be proper. Using these premises, it will follow the rules and come up with whatever conclusions it will it has to come up with. Okay, so validity is something different from truth. Logic deals only with validity or provability. So I can prove Socrates is immortal if I start with the premise that all men are immortal. It can be proved in that logical system. Okay, but it need not be true. Fine. So provability is something entirely different. Because the system is closed, only provability and non-provability are meaningful in this system. Truth and falsity are not relevant to this system. It's a closed system. The moment you speak of truth and falsity, you are opening up the system and trying to match it with reality. Okay, so we will discuss only closed systems. We will discuss only provability or validity. We will not worry about truth or falsity. So even when silence. So even when we discuss truth tables, those values we are assigning, assuming the statement is true, assuming P is true, Q is true. Then what will be P and Q, or what will be P or Q, or what will be P implies Q? Okay, assuming. We don't know whether they are actually true or not. Assuming they are true, then what will be the conclusion? Okay, so a formal system inherently does not tell you what is true, what is not true. It will take the premises as they are and it will give you some conclusions. Okay, truth value, you need to go to reality. In logic, you will only look at provability. Okay, so we'll look at in the next lecture. Bye.